We're getting started on another round of x64 practice programming on Project Euler problems. And this is the problem we've got on our plate to get started tonight. Problem number 16. I'm going to read the problem and discuss it a little bit. We looked at it at the end of last time shortly, so I'm already familiar with it. But I'm going to try to, if anyone's watching right now who didn't catch the last one, I'm going to try to get you caught up on what this problem's all about. So it says 2 to the 15 equals 32,768, and the sum of its digits is 3 plus 2 plus 7 plus 6 plus 8 equals 26. Okay. What is the sum of the digits of the number 2 to the 1,000? So it's given us an example pattern, and then it's asking for the sum of the digits of the number 2 to the 1,000. Now, with something like this, I don't expect that we can do any super crazy math tricks to make this simpler. We could figure out what the first digit's going to be pretty simply, because if you look at what happens when you multiply by 2 over and over again, you would find that it gets into a pattern. 2, 4, 8, 6, 2, right? 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6. So this digit would be very predictable. But I don't think that the rest of these would be very easy to get a handle on mathematically. We might be able to do something similar, like if we look at it with modulo 10, for instance, we might be able to predict the first 2 digits, but every time we raise the modulo, it'll become harder to run that kind of thing, where we'll have to multiply by 2 however many times until we find a cycle. And then when we're doing like 5 digits, the cycle could take, something like, what is that? 5 digits, like 10,000, so at least 5,000 steps to find. And that's only getting us to 2 to the 15. Each time we double, or after every few doubles, we'll add another digit. So I think it would end up at 1,000. It would still need, it would still need more. It would grow outside of the range of what we can handle, and we would still end up needing to process numbers with 1,000 bits in them. So the other thing is, the reason this isn't just immediately trivial to solve is because we have computers with 64-bit integers, and that number right there is going to take at least 1,001 bits to represent using normal representation. We do have a big num that we implemented for a previous problem, and I'll bring that up, but there's a problem with it. So it's only going to be the beginning of our solution. So we built this thing that does these things, right? It's got a U64 by 3, and we can do multiplies and divides with it. We didn't quite do multiply and divide by that much. We did this one. So abbreviated long multiplication and long division using just the U64 as the second input. And we also wrote an adder for these things. But these just go up to 64 times 3 bits, which, let's take a quick look. 64 times 3, that's 192 bits. So to get to 1,000 bits, we would need something with 16 slots. And the way we wrote this one, we can look at how much code would it take to write one that's 16 slots fixed. So let's see. U64 by 3, add U64 by 3. Start with that one. So you can see we have each slot is manually added here. So we have 0 gets added to 0, 1 gets added to 1, 2 gets added to 2, and then we're also managing a carry bit all the way through. So we have a carry bit here, that gets added in. We have a carry bit here, that gets combined here to make a carry bit that we add in here. And so if we did this for 15 steps, it'd be this is for 3, so it'd be 5 screens of this kind of code just to add. Let's see, multiply is about the same length. So probably about 15, or probably about 5 slides of this to go from 3 slots to 15, and then 5 slots of, or 5 copies of this. So what I'm trying to emphasize here is that doing another big num the way we did the first one that does 1,000 bits, or I guess it'd probably be 1,024 bits, if we did 16 slots, that would be a lot of code. I think in order to keep it from being too much code to write, it'll be easier if we actually make it a variable length. So doing something by hand 16 times is quite a lot, but if it's a repetitive thing that could be fit into a loop, then it's actually kind of easier to write the loop than it is to write the sort of spread out 16 copies of the same thing, right? If there's a bug, we don't have to fix it in 16 places and figure out where we did or didn't screw it up. And it would just be more flexible if we end up needing 10,000 bits in another problem. We won't have to write another one where we would definitely end up needing variable length anyways. 16 slots is probably like a little past the max of how far we could reasonably expect to make progress by doing these fixed size ones. So all that is just basically my way of saying I think what we'll be doing is taking what we already know, long multiplication, long division, the abbreviated versions, and addition, which I think we wrote, addition right here. And we're going to generalize them from a 3-slot big number to a variable length big number. So let's write down what problem we're doing here and make some notes. Problem number 16. Find the sum of the digits in the number 2 to the 1,000. So that's the problem. Our plan is to implement variable length big nums. Okay, so what we need is, first of all, we'll break this plan down into, oh, you know what? I'm going to redo that because I didn't follow my normal procedure of zooming in for the notes. All right. Find the sum of the digits in the number 2 to the 1,000. Plan. Implement variable length big nums with add and divide operations. So in this problem, we don't need to convert any number from decimal to big num, right? So we're going to be able to just build our x variable, like 2 to the 1,000 here, the one we're processing. We're going to be able to build that trivially by just setting the 1,000 and first bit to 1 and the rest of them to 0. So building this thing is easy. The only thing we have to do is convert from that number to decimal. So we'll just implement that part for now, since that's all that's needed. But we will be having to design the new structure. So if it's going to be variable length, what that means is, I think what we'll have like a block of memory, And right here we'll have the size. And the size will be a count of the number of U64s that come after that, right? So here are the U64s. And the first one here, so we'll have like a pointer here. Here's our big num, which is a pointer to this thing. It's got a size, which tells us in this case like 4 slots, and then we have like a 0, or I'll call it x. x0, x1, x2, x3, right? So what we are trying to get at here is this side is the least significant slot. Then what we'll do is, so because, okay, yeah, so a couple of things about this. As it gets longer and longer, whenever we do an operation, when we create new numbers, they might become longer or shorter than the numbers that went in. So adding things together. Wait, do I need an add? I think all I need is a divide. I think we just have to implement this structure. Okay. So if we have two big nums of different sizes, then we want to be able to, well, like I just said, we're not actually doing adds right now. If we did have that, we'd have to think about more stuff. But I think with divide being the only thing we have to do, things get pretty simple. I still want to design this a little bit so that it can be expanded to support other operations in the future in case we want to keep using this structure in other problems that might come along. So I want this to be something where we could do add pretty easily. And I think if you had two numbers that both had separate sizes, you would want the small slot to be, or you want the least significant slot to be the first one, because then you can start by just, to do addition or multiplication, you would just start from the left side and go to the right. Like you'd always start from pointer plus 1 slot, right? So this would be 8 bytes, give you the number of slots, and then each slot after that is a part of the count. The other thing we could do is we could say the 0 big num has a size of 0. And the reason we would do it that way is because, first of all, it makes sense, right? As this thing gets smaller and smaller, it uses fewer and fewer slots. At 0, there are no ones that need to get placed anywhere in the array. There are no bits that need to be placed, so why even have slots? The other thing is then you can just dereference up the pointer that we have here, right? This, whenever you're passing big numbers around as pointers, you can do a 0 test very easily by just testing one U64. If that size is not 0, we know that that number is not 0 because we are saying the 0 case will have size 0. In other words, we're saying if size is not 0, then at least one slot is non-zero. And then the most the other thing we could do is basically in the same, in the spirit of the same thing there, this slot never should be a 0, right? Because if I'm saying, hey, I have a size of 4, but then this is all zeros, well, that being all zeros would have been implied by just using a size of 3. So we'll just say the most significant slot the most significant slot is not 0. And then just to be confusing, I put the parenthetical in the middle of the sentence. Okay. Let's go do this, because I don't think it's going to actually be very hard at all. We know divide is the easiest one to implement, so we have to do the divide, and then we have to do the divide, and we have to do the conversion to decimal, and then we're done. So long division, the abbreviated version, here are our notes. We do from the high end first, we divide by the denominator by taking the highest, so we take n2, which in this case was the numerator 2, and in our new system, that'll be the numerator's highest, most significant slot, divide by d, and we get a quotient and an R2. Then we write that out. If there are any zeros, they will have to be in the first Q2, right? Like the first, it's only possible for, the new number will not have more than one slot of reduction, is what I'm trying to get at. You can't go from having 5 slots to 3 slots. You can only go from having, if S is your number of slots, in the numerator, after the divide, you might have S slots, you might have S minus 1 slots. I'm not going to take the time to prove that. I think it's, it's one of those, the proof is just that the maximum divisor isn't big enough, and you can look into the details to convince yourself of it if that's not obvious. But it should work, because when we take the remainder from this and put it on here, this will always be bigger than 0. Unless this wasn't 0 to begin with, right? Like either this will be 0, either this thing will be 0 and this thing will be much larger than d, or this thing isn't 0 to begin with. Of course, that's if n2 wasn't 0, which we already said it wouldn't be. But anyway, so we take the high thing, divide, output the thing we've got. If it's the first one and it's a 0, we don't output it. And then when we're done, we return the new count. Okay, got it. Here's the plan. So this is going to be a new type. Let's come up with a name for it. It's going to be called a U64 by n, and we're going to say that that is going to be the same thing as void, which might seem weird, but basically I just want this to be a void pointer in, actually I'll make it a U64 pointer. Is that a good idea? We'll find out. It's a pointer either way. I'm wondering what the correct idea is for the sort of underlying type here. I think giving it a U64 instead of a void will be nice, because then I'll be able to check for zeros, like I was saying, by just dereferencing it and checking. There it is. There we go. So here's our numerator. Actually, what I'm going to do is I'm not going to have it returned that way. We're going to put the numerator and the divisor there. We're going to put the quotient there. and the remainder there. That's probably a good way to do it. Okay. And that'll be the assembly version. Then this one we'll take a quotient like, have a quotient like that and a remainder like that. And then we'll want a C++ wrapper here. I don't think I had any wrappers for, I did for the decimal conversion. Okay. So the non-assembly version is going to return our quotient that way, or actually we'll use the div r thing we just made, right? Oh, here's a question. Do I want to just modify n in place? That might be a good one. So let's do that. Let's do in place. And I don't need a Q out. And I can just return the remainder. Then I don't need this to be separate for assembly. It can, like, I don't need a wrapper. I can just use that directly. Okay, so I'll put a thing in, and I'll modify it in place using this thing. And if I want one that's a not in place one, I'll have to write that separately as like a wrapper that first allocates separate space and copies or something. Or I'll write a separate assembly version. So I'll get right past the end of all the U64 by 3 stuff. Okay. U64 by n. There we go. Proc end p. Okay, so we're going to have RCX is going to be our n, the U64xn pointer. D is going to be our, or RDX is going to be D, our U64 denominator. And the way this gets implemented is it's going to be very similar to div small. Okay. So yeah, RDX we need to free up. So we're going to move D into R9 or R8. How about that? And then let's see, the code is going to be like we want to do like ni divided by d, right? So first of all, I need to set I equal to star n minus 1 star n. Let's do that. Okay. So we're going to make, who's going to be our I? I guess RAX is not free, RCX is not free, RDX is not free, R8 is not free, so R9. And we're reading out of RCX, 8 bytes. So that is how many slots we have, and we've put that into I. Then what we're going to do is a loop, and that loop is going to start with a test. So if I is equal to 0, go to done. So test R9, and then jump if 0 to done. Okay, now what we want to do is we want to move into R10. Because that's a free register. We want to move into R10. The value at the slot indicated by I. So first I want to do I minus equals 1. So I'll do the test first, then I decrease I by 1. I is in R9. And then I'm going to read the slot n at n index I, which is let's see. N index I is RCX plus I, which is R9, times 8, because 8 steps for to stride with 8, 8 bytes per each element in our array here, plus 8 because the pointer actually points to the count, and the first slot is at plus 8. So that should put our numerator into R10. Then let's see, after we have the numerator, we want to do, so the first thing we want to do is make sure RDX is zeroed up here. Oh, you know what? That's a mistake. I want to put that into RAX, because so our RDX is initially 0. That's the high part of our numerator. This is the low part of our numerator. And then we can do the divide. So that's going to be divided by R8. R8 is containing our denominator. Good. And now RAX and RDX contain the new numerator and the new remainder. So the remainder will just be used to make high bits like that, and we'll say R equals 0 up here, right? And then what we do, and we'll say this is like Q R equals, okay. So now RAX contains Q and RDX contains R. We want to set n at I equal to the quotient we just got, right? So that's move into this slot, the value in RAX, that's our quotient. And then jump to loop 0 to test again. Now, when we're done, the only other thing we want to do is quickly test if the slot at n dot size minus 1 is equal to 0, then n dot size minus equals 1. And that's if n dot size is greater than 0 too. Okay, so let's do those tests. So first we want to say test. Oh, well, we need to get n dot size. So we've filled the memory with the correct stuff, except we need to do this extra check to see if the final slot has a 0 in it now. So we're going to put n.size into R9. If R9, if we compare that to, so we're gonna, if we, so if R9 is not 0, or if R9 is 0, then we can jump to return. And then we want to, let's modify R9 again with RCX plus R9 times 8, not plus 8. So there'd be plus 8 for the size, but minus 8 because the actual size is 1 past the last, right? So if you give me a 1 in the size, then that means I want to do exactly that index, right? The size itself tells me that index number 1 doesn't exist, but index number 0 does, and index number 0 is at 1 offset from RCX because the size is at 0. So then R9 contains this, and then we test that one. And if that is 0, if that is not 0, we jump to return. And then finally we can do, let's actually put that in a different register just because we still want R9. Now we decrement R9 and we store it back out like that. So that should decrease the size after a divide in place. Okay. And then we need to set the return. So the return is going to be whatever the remainder was from the last divide goes out as our full remainder. Okay. So let's make a quick test number here. I'll start by making the number 1. And then we'll do div small in place. There's test 1. Here's our R. There's our divisor. And let's print out that. Well, let's go like this. There's the remainder. And then the quotient. I'm gonna have to write as a loop. All right, so 1 divided by 1 is 1 with no remainder. Let's do 10 divided by 2. 5, okay. Let's do 3 and then 400 divided by 2. So we get a 2 in that 100 in that slot, a 1 in that slot, and a remainder of 1. If I divide all of that by 5 instead, we get that. Okay. So now let's do something where we don't really know what we expect to see. It's going to be sort of big, but it should be a 1 slotter, right? So this is a 1 larger than the largest possible U64. So there's a U64 0, but we said we're using 2 slots, and this higher slot is a 1. So we've incremented 1 from the largest possible value in a single U64, and then we're dividing by 10. So we get that, which, you know, like that could be true, but the good news is we got 1 slot, which is what we expect. What happens if we add in more slots? 2, 3, 4, so 5 slots. That doesn't seem quite right. 6 slots. Interesting. Got kind of like a repeating digit thing here, and then the first one is different, which is not too surprising. I bet if we did 2 slots and they look like this, or if we did, I should say 3 slots and they look like this, we'd see the same thing. Yeah, so those are different, but that's basically the repeating digit of after a divide by 10. So what's an easy way to test if this is working? I mean, it seems pretty good. I don't know if there's an easy way to do it. Like we could obviously like put a 10 here and we should see a 1 pop out. But what does that tell us? I don't know. I suppose we could compare it to the results of our earlier version that we're more confident about. So this one, let's make this a 0, 0, 10. Let's do div small u64 by 3 and divided by, let's divide these both by 7. And then let's compare, there should be a div result, speaking of which, I ended up not needing a div result here. So there's the first one, and then here's the test one. And so this is gonna look like this. This is Z slots 0, 1, and 2. This is Z.R. Div R, we've got Q.V. Got it. Extra comma in the middle. Okay, cool. So I think that's probably enough verification for me. I feel satisfied that we got it up and running there. So now all we have to do is implement a decimal from U64 by n, right? we'll write a wrapper for that. So that the memory management part will be in the style of my code base. If x was 0, else. Now, how do we get a cap? So let's say we want to know what happens when you multiply by 2 to the 64. How many digits do you get? So 2 to the 64 is 19 digits. So if we treat each slot as 20 digits, we should always be safe, right? Yeah, it looks like that would definitely be safe. So what we'll do is we'll say cap is going to be star x times 20. So however many slots we have times 20 goes into cap. We allocate some memory. We call the ASM version that takes in the buffer and the x. We do need to make a copy of x first, so I guess we should do that as well. Because we don't necessarily want this to modify x in place. So we'll need something like yeah, that sort of sucks. Okay, so here's the part that's a little bit tricky that I'm thinking about. I want to be able to treat x as if it's not going to be mutated in this code, right? This code shouldn't have to think about the fact that this function is going to mutate x, which means this function shouldn't mutate x, basically is what it comes down to. You should be able to pass something to it without having to make a copy first. But doing that in the assembly, yeah, this is the wrapper, so I guess I just do it here. And the assembly, doing it in the assembly would be kind of too much. But we're not really going to call the assembly version directly. We're only ever going to call the assembly version through this wrapper. So the wrapper is the one whose job it is to implement things like the memory management simplifications. So we'll have like a U64 by n. So we get x copy. We use x copy here instead of x, but this is actually going to be on a scratch arena. Okay, right, so this calls the assembly version of the decimal converter, gets their final count, it puts that amount back. Good, and then aligns it. Then we set our result and return it and clear out the scratch. Okay, so that all seems good. Let's write that helper that does the copy real quick. And this one I'm just going to write entirely in C++ here because it's very trivial, and the only interesting thing it does is the memory management part. So it would be kind of just passing through to the to the assembly code for no reason, like not even the reason of learning anything. It's literally just we got to do this, like result equals push array onto the arena, push that many U64s, return result, memory copy into result from the X, size of the X, times the count of the X plus 1. Right? So it's just a mem copy coupled with an arena allocation. And then we do need to go implement dec from U64 by n, which apparently we don't need to do. Why is it? I guess it's because we're not calling it anywhere. There we go. So RCX contains out our U8 pointer. RDX contains X, our U64 by N pointer. We want this to be relatively similar to this thing, dec from U64 by 3. So how did this work? Yeah, it has to make function calls, so we have to move a bunch of stuff into non-volatile registers. Let's see here. Yeah, so this was manually making a copy so as to not modify X in place. Whereas here, we're saying okay. So that is what difference. We don't have to make a copy here in the assembly. What else do we have to do? So we have to do a zero check. We'll be able to do that. There's the buffer. So okay, let's do a couple of those things. So R12 and R13 are getting used at the very least. Move the buffer to R12, set R13 to also be pointing at the beginning. We don't make a copy. Now we want to do if x equals 0, go to finish. Test rdx, rdx. Yeah, we need to just move that as well. Move x to R14. Okay. Now, instead of testing RDX, we test R14, because that's the one that's actually not going to get trashed. And we jump if that is 0 to finish. Call div small in place u64 by n on x and 10. So we move into RCX, the value from x. We move into RDX, the value from 10, and then we call our function. Cool, cool. Okay. So that gives us then x gets modified in place to contain the new quotient, and RAX contains the new remainder. So let's do this part. Equals, what is this doing? Yes, so D equals the remainder. That is the part that's, so this is going out to mov RCX. So it's reading into RCX from, okay. We might not need to do that, because we might be able to just use the RAX register in place now. Let's give that a shot. So RAX contains our denominator. Putter equals D. What is that doing? So that's, yeah, that's the part we do need. So AL, that's the A register, the first byte of it, and we're going to put that into R13, which is our putter. We're going to increment our putter. And we're going to go to loop 0. So we go to loop 0, then we test if x is 0 yet. So that right there is our main body of this thing. Set return value to put or minus buffer. So that changes the RAX register to contain the count of bytes we actually used. We rename these registers putter A and putter B. So R12 is the large one, and wait, is it? Yeah, R12 is the large one. Putter becomes putter A. Putter B gets pointed to the buffer. Putter B gets decremented. Oops. And then we enter into a reverse loop. In the reverse loop, I don't think we need to do anything different than what we did before. We're just swapping all the bytes in order. And when we're done, that's it. Okay. So we wrote that part, we wrote the assembly part. In theory, this should be good to go. Let's take a peek. Something bad happened. Let's take a look at that. Okay, so R13, R12, R13 minus R12 is 4032. So it got a full 4032 above the okay, so we need to go look at this. We don't have unwinding working, so what's our cap? So our cap is 60. We're trying to turn this divided by 10, this number here divided by 7 into decimal right now. Let's see. X copy, does this part look like it works? The size we want is 24 bytes, 8 times. Wait, that should be 8 times 4. Whoops, okay. Still not good enough. What else? What else? For allocate, we copy it. Okay, so result, comma, 4. X comma 4, yeah, those don't look different. So there's X copy, and then we make a buffer with 60 bytes in it. We go into here. From here, first of all, we lose the call stack because we haven't written unwind info into this, but we set these both. We test if R14, oh, R14 is a pointer. Okay, so that got written in correctly. R14 is a pointer, so we need to first dereference the pointer. So let's put that into RAX. And then we test like this. Now, is that right? I don't know. I don't know how I could make it easier to find out. But what I could do is put in something whose decimal representation I'm going to know. So let's not do this divide part, because that will only make it harder. Let's start from here. Good deal. Now, what is a good way to get, trying to think, I don't know of any obvious way to get an idea of what the decimal representation is going to be. Sorry, excuse me, for a number that is using more than one slot. Like this should be even. We could test this, right? We could say like, let's make sure that things like this do what we expect. Yeah, so that's looking good. This should be even and bigger. This should be even bigger. Very good. So here we're getting all the digits, right? Now we don't have any easy way to test that the digits are correct when we are using these bigger numbers, but I don't know what else we could do. I mean, we'd have to write a lot more code to test this, right? We would have to, I think the easiest way to test it is going to be to put it into this problem and see if it's the solution. If we try to test this by writing a multiplier and then a decimal to big num converter, so we can convert to decimal from our numbers. We can't convert from our numbers. We can't convert to our numbers from the decimal, right? We can't get number from decimal the other way around. If we could test this more easily, but I don't think I want to go down that road because that would be two more functions we have to write. Let's just hold off on that until we're not sure it's necessary. So let's now do the thing we need to do. So we want 17 slots. The first one will say 16, and then on slot number 16, we're going to put the only single bit that we want. So 1,000 divided by 64 minus 15 times 64. So we get a remainder of 40. So somewhere around 40 or 41 or 39 is the bit we want. So let's think through. If we were doing 2 to the 0, we would set 1, right? If we were doing 2 to the 2 or to the 1, we would set 1 bit shifted to by 1. So how do we do 2 to the 1,000? Right, this would go on and on, right? There's the generalization. So this is going to be 1 bit shifted by 1,000. How do we do 1 bit shifted by 1,000? Well, let's subtract out 64 a bunch of times. So what do we get left over? The answer is 40. So it's going to be 15 slots times 64. So 15 times 64 gives us 960. And so the first 15, we're shifted out of 15 slots that way. On the 16th slot, we want to be at, we want to do 40 more shifts. So we're not doing just 960 shifts, which would be putting a 1 here. We're doing 40 more after that. So 40 more after that goes there. I think that's our number. And now, right, so just to be clear, that's 2 to the 960 times 2 to the 40 is basically what I just did. So by putting it in slot 16, we're getting a multiplier of 2 to the 960 on the value. By doing 1 to the bit shifted by 40, we're getting 2 to the 40, and so those two values are multiplied together, and that's what this thing should represent. Then we get the decimal representation, and hopefully that is correct. And there's like 300 numbers in it. So finally what we're going to do is we're going to add those up. So add up the decimal values and print that. All right, let's see if that worked. Hey, alrighty. That's so cool. That's so cool. Oh man, maybe I'm a little bit tired. I didn't realize until I started programming, but man, I'm feeling all yawny right now. Let's take a look at another problem though. No, I don't want to do this problem. I remember this one from when we skipped ahead to see what else was coming. BYP64, yeah, this one does feel dynamic programming. I think it's going to be pretty straightforward. So if you're talking about the triangle thing that we're looking at on screen right now, find the maximum total from top to bottom of the triangle below. That one is, we could do it. I'm not entirely sure that I'm excited about it. I might skip it. Not that we can't. It's just, for some reason, it doesn't feel right to me right now. It feels like the kind of thing where you got to manage details, and I feel like my head's more in a space to do like difficult but short things, not necessarily fiddly things. Like I think my attention span is not long enough for that problem right now. Ooh, here we go. This one we can do. We just got started on this one. So yeah, let's do this one. This one will fit the theme of what we did on the first problem. So let me read what we got going on here. N factorial means n times n minus 1 times dot 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 times 3 times 2 times 1. For example, 10 factorial is 10 times 9 times so on and so on times 3 times 2 times 1 equals 3,628,800. And the sum of the digits is the number 10 factorial. In the number 10 factorial is 3 plus 6 plus 2 plus 8 plus 8 plus 0 plus 0 equals 27. Find the sum of the digits in the number 100 factorial. So the trick here is that I think we can just use the big nums again. We don't have multiplication, but we can get multiplication pretty easily. I don't think there's going to be any easier way to do it. I mean, there's some stuff you could do to simplify a little bit, but it'd be like minor optimizations. I think the direct approach here is going to be to use the big numbers we've already got and throw in a multiply. Then we can just iterate 1 to 100, multiply it all in, and print out whatever we get and sum it, right? Same basic thing we did here, except we got to do a little bit more work to build the number than just this. Here's how we built the number before, and then here's how we got the result. So we're just going to do this is going to become a factorial of 100. But to get there, we're going to need to write the multiplier. So let's just dive right into doing that. That doesn't seem too hard. Let's do small. Okay, we're going to do C linkage U64 mul small in place U64 by n. Here's our A. Here's our B. If we get that written in assembly, we will be good. We'll do the rest in C++. Mul small in place U64 by n proc A B by n pointer U64. All right, so how did we implement mul? This one was actually a little harder than the long division version, if I remember correctly. Because you have to manage carries and stuff. Overflows, I guess, is probably what it's called in multiplies, but either way. So here's your setup stuff. You do a multiply. So I want to figure out like what the pattern is. What is this, problem number 20? Okay, so for this problem, we want to find the sum of the digits in the number 100 factorial. Those parentheses there just to emphasize that we're not talking about a really excited 100 where the answer would be 1, obviously. Okay. Find the sum of the digits in the number 100 factorial. So here's our plan. Extend U64 by n from problem number 16 to have a multiply operation. Now, what I want to do is take a moment and figure out what the steady pattern is here. So if I'm multiplying two slots, I always have, I'm going to call it x sub I times, or I'll call it a sub I is in one slot here. I have b in another slot. I take those in and I multiply them, and out comes like I'll call this P sub I for the product, and, whoops, can that go away? Okay. That's not quite true. It's more like L sub I and H sub I for low and high parts of the I multiply. And then there's like a carry. This is I, that's high I. So then R sub I, which is like the result, comes from an add that we need like the high I minus 1 right here, right? And that gets added in to this. Let's do circles for the operations. Boxes for the data. Okay, so this gives us that, but that also gives us a carry bit. So if I have a high I and a carry bit, when I go to do a I plus 1 times b, I'll get a new high and low, and I'll add in the high and the carry bit. So what I actually need here is like this carry bit is another thing we add to this. Yeah, and that can't ever have an overflow. Okay. So we have to have like another add. So we want like, that's low. We'll call this the overflow. So maybe I'll call it F overflow I minus 1. Lives right here. And that gets added to the low part of the I multiply. And the way we got this was we had the high part, the high part of I minus 1 and the carry part of I minus 1. These get added together. And we ignore the carry on that add, right? Yes. So the carry gets thrown out. So the flow here is data comes in from the previous step via the carry and the high, the carry bit and the high bit, the carry bit and the high slot getting added together to make a final slot, and then like the overflow slot, and then that gets added to the low part. This goes out, like this gets written to memory. This part gets pulled in from memory, and then these have like arrows from the previous iteration, and these two go on to get added together and make a new overflow slot, and so on. So that's basically this, the full structure of our loop. We need a multiply, 2 adds, and on one of those adds we ignore the carry bit, on the other one we keep the carry bit. The add that keeps the carry bit is the one that came from adding the overflow slot to the low result of the multiply. The one that throws away the carry bit is the one that comes from adding the carry bit to the high slot. Okay, so when we're on 0, we will just want to have f be initialized to 0 already. So this will just be a 0 on the first step, and we'll read in this part, do the multiply, then the add, but the add, we know the add will be useless, but we do it anyway, just so that it's there for the other operations that need to work that way. So really this whole thing is a part of the previous loop. Because then what we're going to do is we're going to say right here is where we do the add to make, this is all from step I minus 1. And then this part over here is step I. So those get added together and create f of I as the final step. Okay. And that goes on to be used in the next step. Got it. So that's the data flow we want to implement on a per loop basis. So let me say like this here. This is our loop. And now what we can do is go fill in some details. So we know we want f equals 0. I don't know who f is going to be yet. We also want I equals 0. Don't know who I is going to be yet. We need RAX and RDX to be free. So RDX needs to get moved into something else. So we'll start with that. Move B into R9. We need RDX to be free because it gives us part of the result of a multiply. We'll make R8, RF, and R10, RI, I guess. And then we're ready to go. So we do loop 0 here. This doesn't have a return like the divide, because there is no remainder to keep, and there's no need to return a high part since we have the ability to grow this thing. I guess what we want to do actually, okay. So we're going to say that in this call, this will actually be an ASM level call. Can we do this one in place? I don't think we can do this one in place is what it comes down to. This will be the ASM level. Let's back this up for a minute. We can't do mul in place, and the reason we can't do mul in place is because unlike before, this has to be able to grow. So we're going to have an out, and the out will be allocated by a C++ wrapper, and then it'll be shrunk down to the right amount of memory. I'm trying to think of if there's a way. So I guess, is it true to say that a multiply only overflows if its highest spot overflows? Or is it possible for it to overflow just from the add? Is this what I wrote here correct? Let me go look at the by hand version we did a while back. Okay. Long multiplication. Here it is. So if this was being done with a 9 and a 9 here, you'd get an 8 and a 1. So that would be an overflow. Even if you put a 9... Okay, how could you make it so that this overflows, but only if the add is there? If you had like a 1 times 9 plus an overflow, that would cause an overflow, right? So how does that actually work? Is that captured in the thing we did? It looks like I had to use carry twice. No, I'm using a carry here. But this over here is actually an overflow. Like the high part of a multiply, right? Then I add those together. How did I compute R1? R1 is just... Okay, so I only had one case where I had to... The hard thing is we did 3 slots, and 3 slots, it turns out, doesn't have to do this quite fully, because there's nothing that is doing both sides of the relay next to another thing that's like that. We never really sat in the steady state in this code. So what this did was it didn't have to think about adding in an overflow to the first slot, and it didn't have to think about getting overflow from the third slot. In the second slot, so in the one slot, we did all the work once, but we don't really see how the handoff works, because the handoff is kind of truncated by the fact that it's a handoff from and to things that don't need to do the full thing, right? So like here, when we're adding up R1, we cut out the thing that C0, like this, the 2 parts of C0, we cut it down to just 1. So this is like C1 bar. We don't have C1 hat in there. And this over here has all of them added together, but we don't see if we care about the carry bit from that. So we don't have an answer here. We have to figure it out from scratch over here. Okay. So the question I'm trying to get an answer to here is, does this fully capture what needs to happen? A multiply of this slot times our small number gives us a low and a high part. Do we just take the low part and add in some more, and then that's our result? I think so. But then what do we do with the overflow from that? The answer is that needs to get added into the next part. Yeah, maybe this is all just fine. It's just a little bit confusing for some reason. There's something that doesn't feel like I've understood it properly. So I want to answer, can you determine if there will be an overflow on the last slot easily? So like if we look at just the simple case of like 1 times 9 times, or 199 times 9, we get 81 here. 9 times 9 is 81, plus that is 89. 9 times 1 gives us 9 plus 8 is 17. So we couldn't just do that and that. But if I were to reach the steady state of doing a bunch of 9s in a row, I don't think I would ever get a 9 up here, right? So if I'm doing 9, 9, 9, 9, 9, right? So it's like as big as it can be in every slot. We still just get 81, 89, 89. Oh wait, that's not true. I have to add in the 8 on the next one. No, yeah, that was right. 89 is adding in the 8. 89, 89, right? So I can't just look at this to determine it, but maybe I can look at the first 2 slots to determine it, but this is starting to feel more complicated than I was thinking. So the other thing we could point out here is this does in fact prove that my code is my sketch is a little bit wrong over here in my diagram from earlier, because it should be possible to affect this number so that like I can't determine it simply from this and this. So what's wrong with the code I have is that high is completely determined right here. But that's not actually possible. That's not true. High can be modified. Oh, maybe I'm adding the carry in there to account for that. So high is not the whole picture, but high plus carry is the whole picture. And carry is the result of the add of low so this is like a 2 slot number, and we're adding in a 1 slot number, and that means this can have a carry of 1, which means we could be adding that to here. That could still have a carry, which could be relevant, right? But I guess this can never be the max. Yeah, so like if this can never be a 9, then this can never be 9 plus 1. So there cannot be overflow there. Okay, this is correct. Got it. Very good. So I think this will be the best I can think of for now. I'd sure love to be able to find a way to do this without having to do a separate allocation for each multiply. One way to do that would be to do a multiply in place until it causes the number to grow, and then copy it and put an extra slot there. Let's try it that way. Yeah, let's do it like that. Okay, I've made a decision. Now we can move ahead. Small mul u64x by 3. What makes this hard is like saying that it's allowed for this thing to grow when you multiply it. We could also say that, hey, we only want it to, One thing we could do is say we want it to, instead of overflowing, we want it to, like, instead of growing the number, we want it to wrap and return the overflow, and then have the U64, like have the reallocation or allocation change happen outside of the main multiply routine. That might be a better design, but it's not what I'm going to do right now because I don't want to try and over-engineer this. And this is the first thing that occurred to me, so I'm just going to do it. And then maybe if I want to refine this, I can explore other options. So we move B into R9. we want to set f to 0, so f will be our R8 register, I will be our R10 register, and then the loop begins. And what we do at each stage of the loop is we read A, so we'll put into RAX from let's see, A is an RCX plus R10 times 8 plus 8, so that gives us our A slot. We multiply, we clear It's kind of weird that in this I was not clearing RDX to 0 more often, right? Oh wait, no, this only outputs RDX. It doesn't use RDX as high bits. Right. Okay, so I do that, and then I do the multiply. So we do multiply by R9. That gives us B times the A slot, and that goes into, so we get like low high equals AI times B. We want to add F to low. Let's see, we're going to compute a new F later, so we can trash the current F after this. So R8 gets the low. We could also just trash the low, I think. Why don't we do that? The low is in RAX. F is in R8. We add those together. We need to, so the result goes out here, AI equals R. RAX, so there's RAX is free, so that just went out to memory. That part's done. The carry bit, we want to get the carry bit. So let's use R11, that's free. Okay, so C goes into R11. And we add high and C together to make F. So we modify R8 to have a copy of R11. We add into R8 RDX, which is our high bits. So R8 is now set up as our new F, and there we have an add, and a mul. So I think we've done the whole loop. Yep, add, mul. That's the full loop that needs to happen. And then we want to go back to loop 0. Loop 0. Okay, loop 0. So that will actually generate the right result, but it'll never stop going, and it's not incrementing, right? So we need to do I plus equals 1. And we need to do if I is greater than size, so it's like that size go to done. We're going to need another register, and we're out of the non-volatile registers at this point. I need a register that can be used throughout the loop. And that's going to be where we save a.size. That way we can do this comparison without having to load memory or anything. So we compare I, which is an R10, to a.size, which is an R12. Jump if that's above to done. Now we're not quite finished, because while this has done the whole thing of this iteration, the final f, what happens with that, right? At the end we get an f pop out. And the answer is, if that's not 0, we grow the number by 1. So we're going to say if f equals 0, go to return. Otherwise, we know f is not 0 in this part of the code, so we're going to set a.size equal to f, R12 times 8 plus 8 gets f is living in R8, and then a.size plus equals 1. That means we ink R12, and then we move that back into memory where we got it. All right, so that should do the trick. Let's do some tests. So I'll keep that for printing the sum later. I guess I'll just keep them both for printing this thing. But let's do 3 mole small in place. So I've got 4. Not sure if that'll be wrapped or not. I have to think about it. But mole small in place. It's going to take x, and let's multiply by 10 and see what we get. Okay, so we got a 10. If I were to put a 1 here, what would I get? Great, so that makes sense. Now what I want to do is I want to see it overflow. So I'm going to say this is a number with one slot, and it's equal to 1 bit shifted 63 times. Okay, that didn't work. If I don't do this, what happens? That works. So did the mul fail to work when an overflow happened? Is that what we're seeing? So let's do it this way. 1,000, 1 million, 1 trillion, trillion squared. Okay, that's too big. And it doesn't work better if I do this. Okay, what if I do this? So that's just wrong, like obviously. It should be a multiple of 10. Here it works because I guess it's not overflowing. So there's a bug when it overflows. We need to go figure it out. So our size is 1, our x is 0, our f is 0, our 9, our b here is 10. That's what we're doing a multiply by. We say if that's above, we jump, no jump. So RAX gets what? Okay, that big power of 10. Multiply by R9. R9 is our 10 here. RAX becomes that, and RDX becomes this. So there's the overflow. We then go, okay, R11 gets cleared to 0. We add RAX, which is our low bits, to R8, which is 0. So our carry flag says 0. Set R11 to contain a byte indicating the result of that flag, so 0. Then we move RAX, which is our low part, out to the slot where we got the original value that we multiplied in. So that goes out to memory. And then we modify H by adding in the carry. So the carry is 0, so R11 shouldn't have any effect. R8 gets 0, and then it gets added in the value from H, which is the high bits, RDX. So our F becomes 5. We increment R10, we jump back up, and now, it went one too far. This should stop here. There we go. Let's just see something here. Can we make some absurdly large power of 10? I'm going to give this plenty of memory, just make sure it will work. Maybe that wasn't enough memory. There, it works. So yeah, 200 digit number right there. Cool. All right, so now let's see if we can do factorial. I'm going to just give this plenty of bytes because I don't know how many it'll need. We'll start it off at the number 1, but it's got plenty of memory to modify that in place. And then go. Okay. Yeah, that could totally be a factorial of 100. That's about as many zeros as you would expect because you multiply by so many multiples of 10 and multiples of 5 and 2. Each multiple of 5 gets you a 0. Each multiple of 10 gets you a 0. The 100 itself gets you 2 zeros. So, yeah, that's kind of what you would expect. 159 digit number. So 648, is that the answer? Yes! Alrighty. Very cool. So there, we are upgrading our ability to handle arbitrarily large integers, which is pretty cool. You know, I think I might have gas in me for one more problem if it's not too tedious or too much code. So, like I said earlier, I'm a little tired, so we'll try to find one more problem we can wrap up without getting too into the weeds on it. Rixian, hello. It's pretty cool, right? It's kind of neat being able to dig into the guts of the computer and make it do more than it can usually do. Let Dn be defined as the sum of proper divisors of n, numbers less than n which divide evenly into n. If d of a equals b and d of b equals a, d of a equals b and d of b equals a, where a and b are not the same number, then a and b are an amicable pair, and each of a and b are called amicable numbers. For example, the proper divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Therefore, D220 is 284. The proper divisors of 284 are 1, 2, 4, 71, and 142. So D284 equals 220. Evaluate the sum of all the amicable numbers under 10,000. Interesting. Sum of proper divisors. So numbers not including n itself. Could we do proper divisors easily? We have a factor table, so we can get a divisor. To get all of the divisors, we would have to take a number, run it through the factor table over and over again until we found out the prime factorization, and then put that prime factorization together in every possible combination to generate all the divisors. I feel like I want to do that when I have a little more brain power. Let's see if there's anything else that we can do just using tools we've already got. No data parsing ones. A perfect number is a number for which the sum of its proper divisors is exactly equal to the number. Now we just skip that. Maybe we'll do proper divisors next time. A permutation is an ordered arrangement of objects. For example, 3, 1, 2, 4 is one possible permutation of the digits 1, 2, 3, and 4. If all of the permutations are listed numerically or alphabetically, we call it lexicographical order. The lexicographic permutations of 0, 1, and 2 are 0, 1, da, 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 da. What is the millionth lexicographic permutation of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9? Okay. So you're talking about sorting them. So this is like the smallest one because we put in the most significant spot the 0 and the least significant spot 2. And then the next one up is what you get when you put the 2 here and so on. That one sounds interesting. What is the millionth lexicographic permutation of the digits? Okay, so what's happening here, yep, let's do this one. Problem number 24. This will just be a math problem. We won't be doing any big reusable tools on this, I don't think. But let's do it. Okay, so the first thing they gave us was this, which I want to write down. So there's the 6 permutations of 0, 1, 2, right? Now we want to figure out how to skip through the space. So if I want to look at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and all of its permutations, I want to figure out how to skip through that space so that I don't have to iterate the I don't want to have to iterate all whatever that would be, 9 factorial possible values and then put them into a sort or something. I also don't want to write like an overly complicated linear scan that would like find a way to do this in order, which we could probably do. It seems like it would be too hard, like a recursive function. So it like takes the smallest free thing first. So here it takes 0 in a loop, and then later in that same loop it takes a 1, and then later in that same loop it takes a 2. We could do that, but it would go in order. Lava lamp 3773. This is problem number 24. We're gonna. It's about permutations. I don't know what part when you joined us, but we're doing problem number 24. Find the 1 millionth lexicographic permutation of the digits 0 through 9. So we're trying to figure out how can we take the number 1 million and treat it as a sort of input to a function that outputs a permutation where those permutations are strictly in order when you iterate them without having to actually output all the permutations. That's what I want to do. So if I were going to write just a generator for this that would generate them one at a time, it would like grab this one. So it'd have a loop that would go like, that loop would go 0, 1, 2. And it would like grab them out of the set. And then it would call a function that like does the loop inside of itself again and goes, okay, well, what's left over? Well, first I'll grab 1 in the loop and then I'll grab 2 in the loop because those are the 2 things that are left over. And so then, you know, eventually you'd have a counter that would count how many times you've done this, and when you got to 1 million, you're done. How can we do better? Well, one thing we can do is we can go like, look, how does this get divided up? This gets divided up into 2 slots here, 2 slots here, and 2 slots here. So there are 3 sets of 2 slots, I'll call it, or groups, that would be better. Three sets of 2 groups. So let's do the next one up. So let's do what happens if we look at 4. So I'm going to write a little smaller here. 0, 1, 2, 3, 0 again, 1 again, but 3, 2, 0. Now we're done with the 1, so we'll grab the 2, 1, 3, 0, 2, 3, 1. And we grab the 3, 0, 3, 1, 2, 0, 3, 3, 2, 1. And then same thing again, but with 1, 0, 2, 3, 1, 0, 3, 2, 1, 2, 0, 3, 1, 2, 3, 0, 1, 3, 0, 2, 1, 3, 2, 0, then 2, 2, 0, 1, 3, 2, 0, 3, 1. No, that can't. Yeah, that's right. 0, 3, 0, 0, 3, 1. Yep. 2, 1, 0, 3, 2, 1, 3, 0. 2, 3, 0, 1, 2, 3, 1, 0. It's getting a little hard to like figure out how to do this. So grab the 3, go 0, 1, 2. Now 3, 0, 2, 1. 3, 1, 0, 2. 3, 1, 2, 0. 3, 2, 0, 1. 3, 2, 1, 0. Okay. So here, we first of all get the same pattern again. So there's 6 groups of 2. But then there are 3 groups of 2, but then there are like 4 groups of 3. 1, 2, 3, 4. 4 groups . 4 sets of 2 groups, no, 3 sets of 2 permutations. Okay, down here we get 4 sets of 6 permutations. And those 6 permutations are subdivided using this right here. So what we could do is number these groups. So this is group number, or set number 0. This is set number 1. This is set number 2. Down here, we have set number 0, set number 1, set number 2, and set number 3. So what we could do is say like, okay, if we're doing permutations of 4, then we're expecting 4 of the digits 0, 1, 2, and 3. So 4 digits are involved. Then we know that we can take this number we're looking for. If we're looking for the 10th one, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we're looking for 10 out of the possibilities with 4 digits, then what we want to do is say, okay, 10 divided by 4 tells us which group we're in. Because, or 10 divided by 6, right? 6 is how many elements there are in the group. So if I'm understanding correctly, 6 is, this right here is from 3 factorial, because that's how many ways there are to arrange the other 3 digits after you've picked the first one. So first you pick the first digit. Yep, this is how we do it. Okay, so we pick a digit for the first slot by going, take the index we're looking for and divide it by the n-1 factorial of whatever slot we're at. So if we're trying to do the fourth position here, then we're going to say divide by 6 because that's 3 factorial. And then whatever group number that gives us, that tells us if we're in 0, 1, 2, or 3. So that becomes digit number 1. But then what happens is the next ones are all shifted, right? So after one gets eliminated, later we could do divide by, we could do the same thing on this group, but we would end up with a bug, right? Because it would think it would get 1 for this slot, and then it would go, okay, here I want the number that is in, I want the group number 1, right? So it's like there will be 3 groups, 1, number 0, number 1, number 2, and it'll identify that it's in group number 1. And then it'll go, okay, I see that there are 2 options, and it'll figure out that it wants to be in option number 1. And then finally, it'll put a 0 down, right? So it would end up with something like this. If I picked a different one to circle, I wouldn't necessarily always get 1s. So guess I can't go too far. Let's just leave that circle on there, but say I circled this one to be interesting instead. So then what we would see is it would go, okay, first of all, the first group I'm in is group number 2. Then I'm in group number 2. Then I'm in group number 0. And then I'm in group number 0. So the question is, that could give us these digits, except that we have to take into account the fact that this is if we were doing a permutation of 3. But if we're in a permutation of 4, it has to get modified. How do we modify that to make it look like 2, and then there's a 0, 1, and 3 are left over, so 3, 0 and 1 are left over, so 0, and then 1 is left over, so 1, right? So that's like, you have this like picker over here, and you're going first select the second spot and then cross it off, right? So okay, let me do this. I'm going to sort of animate it for you. So we have 0, 1, 2, 3 is our palette, and we go get number 2. Number 2, good, and we cross it off. Then we go get number 2. Number 2, 3, and then we cross it off. And then we go get number 0. 0, and then we cross it off. And we go get number 0, and then it goes 1, and we cross it off, right? That's kind of how it works. So this is that, this is that, this is that, this is that. How do we do that with a computer? I mean, we could just keep an array and sort of shift the tail of the array down each time. That would be possible. Another thing we could do is, instead of shifting the array, we could go like 0, 1, 2, 3. And then after we have grabbed spot number 2, suppose I already grabbed number 3. When I grab number 1, it has the effect that the numbers 1 and 2, okay, so like when the number, when the number 1 appears, suppose I just got like 1, 1, the last no digit is always going to be 0 in this guy. So let's make another one of those and think this through a different way. Suppose I looked at 1, 1, 1, 0. And then I have my palette over here, right? And what's in the palette is irrelevant. This could be A, B, C, D, right? But anyway. What I'm thinking about, though, is if these are numbers, we could take advantage of that to do something else. We could go, okay, go to slot number 1. And then we go to slot number 1 and we say, I see that I'm going to be writing down a 1. And now anything larger than 1, and we are now like done with this slot. So then we like chop it off here and we increment each of these. So this becomes like a new array that's 0, 2, 3 by adding 1 to all of these. Right? Does that work? If I then grabbed 1, it would, if I follow it through both ways, so I cross that off. Then I do 1, I grab a 2. So I go here and I go, all right, I need to increment everything there and afterwards and chop it down. And I go 1, that gives me 3, chop it down, and then 0. So that works. But what if, it seems like something could go wrong. What happens if I put a 0 in earlier? Like, let's do that. So it goes up and back down instead of just going down at the end. Forgot to do that one, but so let's go. Here's my palette, 0, 1, 2, 3. Slot number 0 has a 0 in it. We cross that off. When we rewrite, we are adding 1 to 0, 1, and 2. 1, 2, 3. Oh yeah, this definitely doesn't work because like if I had something larger and I grabbed a 4 and put it in at the beginning and then later I grabbed 3, I shouldn't then have 4 in the palette. I should have like 5. But how would I know that? The only way to know that is for the 3 to look ahead and see that 4 has also been used. So no, that just doesn't work. We can take that back. Is this sort of scratching out the palette thing the only good option, really? Is there another way? I think that's the best way I could do it. I can easily get the first digit correct using this method. And I think if I repeat that, I will get stuff like this. Whoops, that's not what I meant. I will get stuff like this if I repeat this method multiple times. And then I would have to do something like this. I just don't think there's any other way I'm going to be able to really figure out to get the digits from the group numbers. Okay, so that's the plan. All right, that means I need a few tools here. So let's crank out a few tools. So first of all, let's get a way to fill out a table for factorial. Fibonacci stepper, choose. Okay, fill factorial table. Boom, boom, boom. And then we just set like I equals 1, or let's use I as our iterator. Or, no, let's do one past last equals RCX equals N plus C. Let's start with that. Actually, let's do this. Table count, table count, table count. RAX is going to be RCX plus RDX. Okay, times 8. So there's our offset. It's where we want to stop. And then let's set n equal to 1. Then we'll have a loop. That loop will go if putter is above or equal to the one passed last, go to done. So compare putter, which is in RCX, to one passed last, which is in RAX. Jump if that is above or equal to done. Okay. And then what do we do? We're going to write n, so we're going to take putter equals n. That's what we want to do. Move into what our putter is RCX from R8. Okay. And then we want to do, we still need an I, so that was kind of useless. Yeah, this was useless. All right, rewriting this part. So, I greater than or equal to count means we're actually comparing RAX to RDX. Then go to done. This becomes table I equals n. So RCX plus RAX times 8. R8 is Rn. And then we want to take our n and multiply it by, okay, first we are going to take I plus equals 1. And then we're going to take n times equals I. Multiply 8, R8 by n, RAX. And then go to loop 0. Okay, so this loop is pretty simple. Just right out to the table, increment I, and then multiply n. Test if we need to keep going, and there we go. So that should fill in a table of factorials for us. Fill factorial table. Here's our factorial. Give me 10 of those, and then let's just take a quick peek to make sure we got it right. That looks like a factorial of 0, which is not really what I want. But it makes sense that that's what I got. So I want to when I equals 0, we're writing to slot 0, but I want to treat that as I is 1 and multiply by I is 2. So I really want to have like Maybe this is the way to do it? I don't know. Yeah, that's better. I have no idea if this is better than like having a separate variable or what I would do there, but I mean, I could do like this. We add 2 to the variable, do the multiply, subtract 1. That way it's maybe better than using an extra register to accomplish the same thing and a move instruction. I don't know. I would have to do 2 additive arithmetic things anyways, but they could both be inks instead of an add and a dec. So I have no idea the pros and cons there. Probably were fine. Not much to improve on there, I'm gonna guess. So that fills out a factorial table. We need that just because I didn't want to have to do any divides or do the factorial function over and over again. I might as well, if I'm going to build a factorial for, factorial of 9 and then use factorial of 8, I might as well just get them all in one go. So there's my factorial table. Now what I want to do is, the rest of this isn't even like reusable super much, right? Like, I guess we could do the thing that deletes something out of an array in assembly if we wanted. Yeah, let's do that. That sounds fun. So we're gonna say U64 array index. Okay. So we're gonna write a function for dealing with dynamic arrays. It's not going to be a dynamic array that can resize itself for now. So let's see, RCX is going to get the array, which is a U64 pointer. RDX is going to get the index, which is a U64. If index is less than count, greater than equal to count, go to skip. Say RAX, so count equals array count. So we'll put the count in the first slot of the array. Or we could do this like STB style. How about that? So our array will have a backwards slot for the count. And then if we compare the index to the count, and we jump if that's above or equal to skip. Okay. Then what we do is we say, and this is just going to be a call to mem move. I don't know. Let's go for it. So yeah, call memMove on RCX plus. See, if I'm deleting an index, then I want to move the memory to that index, RCX plus index plus 1, and then count minus index minus 1. if index plus 1 is equal to count. Okay, so first thing we're going to do is say array.count equals count minus 1. Then I see what we'll do. So we'll subtract from count here. New count equals count minus 1. Mov into rax, dec rax, there we go, new count. And we'll store that out. And then we want to call memMove. So I'm going to just take a shot in the dark here and say maybe we call this without any trouble, right? We just do, I guess we're going to have to move RCX into a different register here. So RAX is our, yeah. We'll move RCX to R8, and then we'll do load effective address. So we set RCX with R8 plus index, which is RDX, times 8. We load into RDX, R8 plus, we're going to lose index too, R9, so yeah, move array to R8, index to R9. So we're just moving them out of the way so that we can make another function call. Count minus index. So that would be into R8. We want to do count, which is RAX minus I don't know if it'll let me do a minus, but I'll try it. Minus R9. Oh, but that's got to be multiplied by 8. Times 8. So shift to the left 3 times the R8 register. You let me do a minus? Nah. Nah, you won't. Okay, so that's fine. R8, who's got my count RDX minus R9 times 2 to the 3? Okay, so let's see if we can get it to call memMove from the standard library. That'd be kind of an interesting thing to get working. Directives. Prototype is a function or procedure. You can call the function prototype by the protodirective by using the invoke directive. This sample shows a proto declaration for a function named add_up3 that uses a near call to override the 16-bit model default for procedure calls and uses the C calling convention for stack parameters and return values. It takes 2 arguments, a word and a var args. Add_up3 proto. Let's just try it. So it compiled and linked. Let's see what happens if we darray delete So we're going to do, this is going to be an 11 now. Fact memory. These should just be U64s. Fact memory plus 1. So there's the 10. And then we'll have this be a 10 here. We'll have this use we'll do that again in a minute after we dearray delete number 5. Crash. Okay. Not that surprising. Let's find out why. Can you show me like more about when you crashed? Assuming you made it to this. You called something. So let me just check and make sure that like when that happens and then I try to get to the return instruction, that's where the crash is. Okay. So it is just a crash in trying to implement or trying to call this. Let me check the parameters I passed. RCX, RDX, R8. So I have 2 pointers and then that thing is way too huge. Way too huge. I can't use RDX there. What was I thinking? What is count? RAX. Okay, did the 5th one get deleted? 1, 2, 3, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So 120 is there, and 720 is this. Okay, so that'll let us delete the spot out of an array and shrink the count on it, one at a time. So that's cool. So the final thing to do is just take our number and subdivide it 10 times using this pattern here, right? So that'll just be like, we can do that in assembly for practice, but it won't be a super reusable thing. So we'll throw that into a little throwaway function here. Euler 24. This is going to take the fact table and some label array and return a U64. So let's do that. Let's see. Euler 24 proc NP RCX will have our fact table, which is a U64 pointer. RDX will have our label array, which is also a U64 pointer. At the end, we're going to want to return the answer to the problem, which is the millionth permutation of a 10-digit lexicographically ordered set of permutations. So there we're going to get our factorial table. Here, let's get our label array. It's going to look like this. One I less than or equal to 10. Label array I equals I minus 1. I plus 1. I 0 I is less than 10. There we go. Let's do it that way. So then our answer is just Euler 24 called on fact and label array. Very good. Okay, so we're going to write the assembly to solve the rest of the problem. So let's see. Oh man. Let me think. So the first thing to do is we need like a loop. And we need to like sketch out and figure out the structure of that loop and when it does stuff. So it needs a counter, and we're gonna have that counter start at 9, right? So 9 because we're starting with factorial of 9, which is in the table at, wait, I got, divide by 2, divide by 1. So it's divided by 9 factorial, 8 factorial, 7 factorial, 6, 5, 4, 3, 2, 1. Oh, the last digit. Okay, so when there are 3, okay, something I had not appreciated. When there are 3 digits, you divide by 2, because it's factorial 2, that's 2 digits that you're flipping back and forth. So when you pick this digit, that looks like the last choice you have to make, but technically you still have to place this digit. So you're placing 3 digits, you're only making 2 decisions. Okay, so we start with I equals 9, because we have to place 10 digits, but the last digit will be placed outside of the loop. The loop is for doing a decision and then place a digit. Make a decision, place a digit. The last digit gets placed without a decision getting made. I mean, a different way to look at it is we're just going to end up dividing by 1 the number that's already going to be 0 and get a 0, right? So that's why we're not putting the last step in the loop. Okay, so 10 factorial of 9's at index, let's see, index 0 has factorial 1, index 1 has factorial 2. So really we should start with I equals 8. That's where we will find factorial 9. So put an 8 into that register for our I. And what we will do is at each step, we want to take, we're going to have some n, we'll call it index, equals 1,000, 1 million. So that'll be our 8, 1 million, our index. And what we do at each step is we take our index and we divide it by the number of permutations. We divide by the number of permutations. So we want to first get the number of permutations. Perm count equals fact table I. So let's move into R9 from RCX plus RAX times 8. So there's, oh, and we want to do that as a 8-byte read. So that grabs 8 bytes from the table and puts it into R9. That's how much we want to divide the index by. So we used RAX. We're gonna have to move things around. We do have to do divides this time. So move label array into R10. And then I can't be RAX, so that'll be R11. So there we go. Fact table index I. That gives us our permutation count. And then we want to do, I don't know, like Well, we could possibly use RAX for the index. Okay, then we're going to do index equals index divided by perm count. Right? No, we can't do that. We don't want to trash the whole index. Right, so let me think this through. What we're doing is we're saying first we divide. Oh, the new index is the remainder. Okay, got it. So when we divide, we'll get a group number and we'll get a remainder which tells us what the sub-index is, right? So yeah, we can put that into RAX. And then what'll happen is we'll do group index comma new index equals index divided by perm count. So then we do clear rdx to 0, divide by R9. So R8 or RAX and RDX are the high bits of the divide. We do the divide by the perm count. And now RAX contains the group index. And that tells us what we need to emit as oh, I don't need to output a U64. I need to output a permutation. With 10 possible values there. Let me put that there, so I'll be sure. Euler 24. That's a little frustrating because that means that I have to use this register too. So R8, well, luckily R8 wasn't being used for anything, so it's actually fine. Okay, then we want to emit let's just write what we're doing. Perm out equals label array group index. You know what? I just remembered I have to do function calls here too, so I might as well just preemptively start grabbing non-volatile registers at this point because it'll be faster to do it that way. We'll just grab these. So U will be R12, U will be R13, U will be R14. U can be R8 because it doesn't matter anymore after the function call. Factorial table R12. So I need to move fact table into R15. Move to R15, RCX. Okay. So R15 is our factorial table. R11, no. R14 is our I. So that gives our permutation count. We need to move into RAX the value from index R12. Do the divide. Now RAX and RDX contain some results that we care about. the group index tells us what to output, what to emit. So then we want to go, let's see, RCX is free. We'll grab that. Actually, R8 is also free. Let's grab R8. We're going to put into R8 I'll take it back. We're going to put into RCX just so I don't get confused. The value from, let's see, we want to do this read first. Label array is R13 plus group index is in RAX times 8. That's a 8-byte read. And then we do a write. So we want to write into I need another one. 12, 13, 14, and 15 are all getting used. Yep, we need more. Grab me another one. And then move perm out into our SI. Okay. So we move into that pointer, perm out from label array group index. So label array group index happens here, put into RCX, and we connect that back out here. Done. Then what we do is we take the perm out pointer and we increment it. Perm out is an actual pointer, not an index. So what we're going to do is add RSI 8. There we go. Alrighty, getting there. We're getting there. We output the thing. We increment the pointer. Then we need to delete. So we need to call. Before we do the call, let's save, because we still have the group, or we've used the group index. We haven't used the new index. So we're going to say index equals new index right here. New index is living in RDX still. So we'll make index, which is R12, RDX, which has the new index we want to use for the rest, right? So like if we were looking for number 10 here, then after the first divide, the remainder was 4, which went into RDX, is the index we want to use when we use this as the main set, and subdivide it by 2, or divide it into the 3 groups of 2 after that, right? Okay. Index equals new index, and then we want to call darray delete. Darray delete will take our label array and the group index. Group index is still in RAX at this point. So move into RCX. Where does label array live? Label array lives in R13. And then we move into RDX. Where does group index live? That's in RAX from the divide. We call darray delete. And then what else do we have to do? Done the emit. We need to I minus equals 1, right? That's telling us that's our counter there. And we want to do a test. So if I, so we want to do 8, 7, 6, 5, 4, 3, 2, 1, 0, right? We want to do if I is less than or equal to 8, go to loop 0. So test R14 against 8, jump if that is below or equal to loop 0, right? So the reason for that is this is an unsigned comparison. So when it's at 0, it will still be true. And then when we decrement it from 0, we'll get an overflow, and then the loop can stop. So when the loop is done, I said there was something else we have to do. So that emits everything but the final label. So finally what we want to do is perm out equals label array 0. So we grab this and we're just doing label array 0, gets the perm out there, and that should be it, right? That should be it. Here we need a loop to print out all of the permutation labels. And crash. Okay, let's check it out. I think we're done with this. So R9 is just wrong, the wrong register there. That should be R8. Aha! That is a permutation. So let's do a little bit of testing here. Let's start by saying, what if we just ask for number 1? 0, 1, 2, 3, 4, 5, 6, 7, 9, 8. What if I ask for number 0? So there it is in order. What if I go 1, 2, 3, 4. This looks like it's working to me. 5, 6. Now the 6 is no longer the top thing, right? Yeah. 7, 6, 8, 9. 7. Boom. So let's see. There were 4 times 6, so 24 is the next time it's interesting. At 23, we still have a 5 there. At 24, yeah, the 6 pops in front of the 5. Okay, so I'm willing to say that that looks good. So let's pop that in and see if we got it. Oh no. Where did it go wrong? Where did it go wrong? Well, this is one we could actually just do by hand too. So let's do it by hand, and then we'll fix our code afterwards. So I'm gonna just start dividing these out. And I'll write down the results. I'm gonna use a calculator here that you won't be able to see. So we're gonna take 1 million. There is one thing I should check. I just realized. 1, 2, 3. Let me just check one fairly obvious mistake I might have made. 1, 2, 3, 4, 5, 6. No, okay, that's a million. Maybe the 1 millionth is actually the index number 999 though. There we go. There we go. Okay, we don't have to do it by hand. We got it. We got it. So thinking about that, it almost feels reusable. Like this could have been the permutation indexer, right? It doesn't do anything so crazy that we couldn't keep it around and call it the permutation indexer. I might want to just inline this darray delete part. That feels reasonable to me because I don't really want to leave that sitting around. But like the rest of that was fine. We could do the rest of it that way. I would just say like pass me the index that you want and memory for the label array. I will set up the label array myself and I will inline this to myself. Maybe I'll do that some other time though. I'm feeling pretty tired. That was good, but I won't delete this one. I think we want to actually pull something out of this. So maybe I'll get started on that next time. But yeah, let's wind down by peeking at other problems we might work on next time too. So there were some that I skipped. I really don't like this one. It asks you to count the number of letters in the like English spelling of numbers, but it's not even like, 1,000. You have to put the spelling of 1,000 in, and so you have to like figure out the exact spelling, like and whether or not and is included is 342. I don't know. That sounds like a bunch of rule writing. This one could be good. Some data processing stuff. It's just like a little optimization puzzle on a table-driven thing, I'm pretty sure. Like you figure out the shortest path, or you figure out the best sum you can achieve at each node, and then use that to calculate further nodes down. And the hardest part is probably actually like figuring out a regular way to do the indexing into a triangle. Like, I don't know. We could do that one. That would be a quick and easy one, probably. Skipping that one as well. Well, this one isn't as bad as the other one. It still involves some amount of nonsense, but they actually define all the nonsense for you. How many Sundays fell in the first of the month? It doesn't feel as exciting as like the big nums and stuff like that. We did this one. Ah, yes, proper divisors. The sum of proper divisors and perfect numbers. A number n is called deficient if the sum of its proper divisors is less than n, and is called abundant if its sum exceeds n. As 12 is the smallest abundant number, the smallest number that can be written as the sum of two abundant numbers is 24. By mathematical analysis, it can be shown that all integers greater than 28,123 can be written as the sum of two abundant numbers. However, this upper limit cannot be reduced any further by analysis, even though it is known that the greatest number that cannot be expressed as the number of two abundant numbers is less than this limit. Weird. Find the sum of all the positive integers, which cannot be written as the sum of two abundant numbers. So yeah, one way to do this would be to just, if we had a thing that could give us divisor sums, we would just do a single iteration each step of the way. We'd get a divisor sum and compare it, and then we'd be done. There might be better tests for deficient numbers, but I kind of doubt it. Big numbers were just more fun. So one thing is I can't do problems outside of problem number 1 the first 100 problems, because they put the like, they don't want you to share solutions for problems. So I'm keeping all of my on-stream solving to this block. Just follow their rules. What is the index of the first term in the Fibonacci sequence to contain 1,000 digits? That we could do. We could do that one right now. Well, not quite. To do that one, we would have to extend our big num system with adds, but we could do that next time very easily. I think that was the next one in order, right? Yeah, we could do that one. So we could do divisors, we could do more big nums. I'll go read the problem you suggested though, because I am curious. 375. Let S sub n be an integer sequence produced with the following pseudo-random number generator. S sub 0, S sub n plus 1 equals S sub n squared mod that number. Let aij be the minimum of the numbers. Let mn be the sum of aij. M of 2 billion. Ij, minimum of the numbers Si. So this is the minimum of some sequence, some subset of this. This is the sum of all of the sequences that you can form under some range. Wow. I think I would need to do some problems before this one to like build up understanding of whatever that's relying on. I know what all the pieces mean, but I would need to practice some of the concepts to even wrap my head around how to solve that. Yeah, this one here, what is the index of the first term? So yeah, we could solve this one in a closed form way actually. But what's the fun in that? I mean, it would be pretty easy though. Using the phi to the n trick. Where is that? Did that a long time ago. Phi to the n over root 5. So yeah, this is the thing you were thinking of. We would have to do f of n, which is approximately equal to phi to the n over the square root of 5, is greater than or equal to 10 to the 999. Yeah. And then we'd solve for n there, you'd get an answer. Wanna try it? Let's do it. Well, my calculator can't deal with 10 to the 999, so I can't do it that way. Yes, log of both sides, that's a good idea. So log of n log phi over n 5n. Okay, why don't we do this? This sounds even intrigues me. I will do this one by hand, no computer involved, because it almost seems easier to do it that way. Although it is depriving me of a chance to write an adder for my big num system from this stream, but the fact that it seems like it has a closed form solution is pretty cool. Okay, here we go. We want to solve phi to the n over root 5 is greater than 10 to the 999. Greater than or equal to, right? Yeah. Let's see. Why did I write that so big? Let me zoom out a little bit so that it'll look smaller. So we want to do a little space I can get cozy up on here if I'm gonna do some heavier math. Log of phi to the n over root 5 is greater than or equal to log 10 to the 999. Then log rules, so n of log phi minus log root 5 is greater than or equal to 999 log 10. N is greater than or equal to 9, 9. Let me get myself a little more space here. N is greater than or equal to 999 log 10 minus or plus log root 5 all over log of phi. Okay, and do I have phi saved on my calculator still? Let's see. That looks right. Yep, that's the one. Okay. So plugging this into my calculator, I'm getting 999 times log of 10 plus log of the square root of 5 divided by log of phi. So that is approximately 4781.8. So we could try 4782 and see if we have a solution. Here's the rule right here. Members found to be spoiling problems beyond the first 100 problems will have their accounts locked. If you're keen to share your insights or wish to see how other members solve the problem, visit the thread. Anyways, thanks folks. That's where I'm going to wrap it up for tonight. Next time it looks like we'll be doing some problems involving generating lists of divisors for numbers, so some divisibility stuff. Going back to the prime numbers and the factorization tables we have. That'll be next Tuesday, and I'll see you guys then. Thanks. Bye.